In September 2016, NASA's OSIRIS-REx spacecraft began its 2-year journey to the asteroid Bennu, and this past December, it finally entered Bennu's orbit. Because scientists are pretty smart, though, they started collecting data on Bennu long before OSIRIS-REx officially got there, so now they are ready to start sharing their preliminary results. This week, researchers published 7 papers about Bennu across 4 journals: Nature, Nature Astronomy, Nature Geoscience, and Nature Communications. There's a lot to talk about there, from updates on the asteroid's density to its chemical composition, and while we don't have time to unpack everything, we will give you some highlights. Because it turns out that Bennu is not entirely what we expected. Bennu is kind of special as far as asteroids go. We knew before we got there that its chemical composition is similar to that of meteorites that formed at the beginning of the solar system, but Bennu is a lot more pure. Those meteorites changed as they got knocked off whatever parent body they came from, and they became further contaminated by interacting with Earth's atmosphere and the ground. But that hasn't happened to Bennu. So when OSIRIS-REx returns a sample of its surface in 2023, we will be able to say more confidently what the chemistry of the early solar system was like. Except this mission has also revealed that taking the sample will be harder than we thought. As part of their research, scientists refined their estimates about Bennu's mass, volume, and density. Like they had previously suspected, Bennu isn't very dense at all, which supports the idea that it's just a pile of rubble instead of a hunk of rock. That part wasn't surprising because other near-Earth asteroids around Bennu's size are like this too. During their lifetimes, these objects were likely obliterated through one or many collisions. Then over time, those rocks came together until they were one asteroid, tenuously tied together by gravity. What was more interesting about Bennu is that not all of its rocks seem to have come from the same place. OSIRIS-REx found that they come in a variety of colors and shapes and reflectivities, which suggests that they came from different places and underwent different evolutionary processes. Some of them likely came from whatever parent body Bennu originally belonged to, while others could have come from rocks that collided with the asteroid over the years. At first, that sounds awesome for sample collection, since it means that we could study multiple rock types with one mission. The problem is, some of the rocks OSIRIS-REx detected are more than 20 meters tall, and there are a lot of them. That means that there are very few safe regions large enough to bring the spacecraft down to the surface to take a sample. Realistically, though, this doesn't mean it's all over. Japan's Hayabusa 2 mission is currently studying an asteroid with boulders like this, and it managed to find a safe place to take a sample. So OSIRIS-REx will likely be fine. Sample collection is just gonna take some time. Still, if and when we figure it out, one thing is for sure, it's gonna be worth it. Because among many other things, our closer view of Bennu has also allowed scientists to figure out the asteroid's age, and this thing is old. After analyzing a set of what are probably large impact craters, researchers estimate that parts of Bennu's surface are anywhere from 100 million to 1 billion years old. That's around a fifth as old as the solar system itself. One of the ways they figured this out was by counting the number of craters of different sizes. Larger craters require larger impactors, and those become more rare as time goes on. But it's not an exact science because there are plenty of other things that can determine how big a crater is. For example, if an impactor hits a soft surface, the crater will be larger, but if it hits a porous surface, the crater will be smaller. We're still figuring out some details about Bennu's texture, so like with almost everything else, we will have to wait for more data to come back to say anything for sure. So these papers have talked about Bennu's chemistry, its size, and its age, but they've also talked about its shape and spin, and the results there aren't any more normal. Bennu is shaped like a top, and it spins like one too. Before we launched OSIRIS-REx, we had evidence that the rate at which it spins has also been increasing, but new results from the mission have been able to confirm that. The researchers also concluded that this increase is likely caused by something called the Yorp effect. This is where the heat an asteroid absorbs from the sun gets re-radiated at angles that generate torque. This is a small effect, but it adds up over astronomical time, so now Bennu is rotating once every 4.3 Earth hours. And that isn't just a cool stat, that spinning creates centripetal force, which combines with Bennu's gravity to affect all of the particles it's made of. For one, it means that the overall force pulling particles toward Bennu's center of mass is roughly 3 times greater at the poles than it is at the equator. In other words, you would weigh 3 times more at Bennu's north or south pole than you would if you were on its equator. That is very weird. The spin also means that a pebble rolling down from the North Pole to the equator would build up enough velocity to literally escape Bennu forever. That seems like it should be a mechanic for a Super Mario Galaxy game, but it's a real thing. Gravity is nowhere near as strong on Bennu as it is on Earth, so seemingly weird stuff can happen. Also, this phenomenon can most likely explain the asteroid's weird shape.
Rocks that roll down Bennu starting at lower latitudes could still fly off the asteroid, but instead of disappearing forever, they'd likely stick around in orbit for a while and then fall back down.
That would help redistribute Bennu's matter over time, contributing to its shape. So far, OSIRIS-REx has proven that there's nothing boring about Bennu, and that even small objects in the solar system have a bizarre and fascinating history. And if we're learning all of this from only the preliminary results, we're gonna have a lot to talk about once the spacecraft brings us a sample home. Thanks for watching this episode of SciShow Space News. We make an episode like this every week, and we couldn't do all this research and production stuff without the support of our patrons on Patreon. So if you are a patron, thank you. We appreciate you, and you are making a difference. If you want to support this show and help us make more content like this, you can go to patreon.com/SciShow.